second part here, second part of the first part, is again a lightning introduction to cement production. I mean, I can't possibly tell you everything there is to do with cement production. Hopefully at the end of this, you've got a kind of broad general impression, and more importantly, you know what's in that grey powder. Because up to now, we've just talked about cement as being grey powder, and in terms of working with cement, paste and concrete, we've got to know more precisely what's in that grey powder. And the first thing I'm going to tell you about, which causes massive confusion, is that, you know, cement chemists like to be different from everybody else, but it's not really that. They like to not have to write down these symbols. And so they've developed this cement chemistry notation here. So I hope most of you have met this already. But it's very important because every time we write C, it doesn't mean carbon, it now means calcium oxide. And when we write S, it doesn't mean sulfur, it means silicon dioxide. A for alumina, F for iron, H for water, S bar, or sometimes dollar, for SO3, and C bar, or something like this, for CO2. So this is the basics. There are others, but you need to know that. Right. Historically, I think it's quite interesting to look at how cement's developed, and basically was known for a long time, even since ancient times, is what's called lime. Now, lime is what you get when you heat up limestone. That's why it's called limestone. Okay, so limestone calcium carbonate. You heat it up about 800 degrees or so. Why is this going on? Is it working now? Yeah. Okay. So you heat up limestone to about 800 degrees, and the carbon dioxide is given off, and you end up with calcium oxide. This calcium oxide you can then mix with water, and it gives you this compound that's called calcium hydroxide. We're going to meet that again later on. But this compound calcium hydroxide isn't very strong. So you mix it up with water, and you get a very fragile material, and then over time that recarbonates, it reabsorbs CO2 and goes back to calcium carbonate, and that's what gives you something, but it's still not a very strong material. So this was basically what was used in kind of building big cathedrals as the joints between stones and things like that, known for a very long time. But importantly, this would not work underwater. So in 1756, Smeaton, who incidentally was the first person to call himself a civil engineer, he came across the fact that if he had lime which contained clay, then he got what's called hydraulic properties. Hydraulic means that it sets underwater. Okay? And he used this to build the Eddystone Lighthouse. This is a picture of the original Eddystone Lighthouse, and mainly he used this in the foundation here. And even though they've replaced this lighthouse, the original is now on the shore, the base of his lighthouse is still there today, still in quite good condition after, 250 years. And then you see sort of things evolve quite slowly. By 1796, somebody called Parker patents what he calls Roman cement. So this was meant to be cement like the Romans, but in fact it wasn't at all. And he made this from calcination of natural deposits which had mixtures of clay and limestone. And then Vicker took this further. He really did quite a bit of scientific work that more precisely identified that clay, it was the role of clay that really helped to make a cement that could be much more resistant to water. And he made this so-called natural cement from a mixed deposit of limestone and clay. And in fact, there's still a Vicker cement company that still makes natural cements in this way near Grenoble. And then finally, we come on to 1824, which is very significant because this was when the marketing guys got hold of everything. And this guy, Joseph Astin, realized that the most sought-after building stone of the time was Portland building stone. Portland building stone that comes from Portland Bill in the south of England. That's a photograph of the natural deposit. And he said, I'm going to call my cement Portland cement because it looks as beautiful as this Portland building stone. But in fact, it wasn't until about 10 years later that one of the workers in his factory realized that the really good stuff was the stuff that was overburnt, that had gone up to higher temperature, and it was really his discovery that led to what's really modern Portland cement. And then around the same time, William Astin, the son of Joseph, he persuaded Brunel, another very famous civil engineer, to use this cement to line the tunnel he was building under the Thames, to put this between the bricks. And there, you see, it was used first of all for this property of excluding water, of water tightness, avoiding the water coming through into the tunnel. And at that time, the cement was made in these kind of kilns, so these kind of beehive kilns where you put different layers of the clay and limestone and the fuel, which would be coal or something like that, and then you fired the whole thing up, and afterwards you dug out your cement. Now, there are still places where cement is made like that. In rural China, for example, they still have a lot of these kilns, but nowadays we have this rotary kiln that I showed you earlier. So this is a diagram of a modern cement plant. Three important components. First of all, we have the quarry here, and this is very important because a cement plant is a very big capital investment. Just for comparison, if you build a car factory seems like a big capital investment, but if you're making cars in that factory, you can basically earn back the money you spent to build the factory in 5 years or so. If you build a cement plant, the cost of building the cement plant means that you've got to be operating that cement plant typically 20 or 30 years before you earn back the money. And that means you've got to make very sure that you've got enough limestone to keep supplying that factory. So the quarry is really very important. And then typically now they have a kind of conveyor belt system to avoid pollution, etc., which conveys the limestone to the plant. And there they mix it with the clay and all other things. We're going to see that in a bit more detail. And then it gets fed into this rotary kiln. This is basically a long tube which rotates. Okay, so this is rotating. And at one end of this kiln, there's this big flame. So you see this kiln is slightly inclined. So as it rotates, the material moves down towards this end, and as it's moving down towards this end, then it gets hotter and hotter. Okay? So finally, in this zone here, the burning zone, you get all the reactions going on that are of interest, and then coming out of this end, you get the clinker. So the clinker goes here, and then you put in the various additions, you grind it up, and that gives you cement. And all this stuff here, this is all the heat exchanging process. This is really the technology that's come in over the past 30 or 40 years, which now means that cement production can be a very efficient process. So that's a diagram. This is a photograph of a real plant. You can get an idea of the scale of it. I mean, this kiln is really big. So these are your houses here. This is your cement kilns, and you can really see that it's a big thing. There's another one. You also see that these are often on railway lines because you've got a material that is produced in very big volumes, so transport becomes very important. So where do we start from? Well, we start from what's called the raw meal. And as I've already said several times, the basis of this is limestone. It's about 80% limestone. The limestone is usually pretty pure. It's usually about up to 95% calcium carbonate. When we dissociate off the CO2, that reduces nearly by half to give you the calcium oxide. The main impurity we have is magnesium oxide, or magnesium carbonate more correctly. And as I've said, having a good supply of lime determines the location of the cement plant. And then we want to have silica. And as we'll see later on, it's the calcium silicates which are really the most important in cement. So we need a source of silica, but the most common source of silica, you also find there's aluminium and iron associated with it. But that's not the only reason why we use clay, which has silicon, alumina and iron together, because this alumina and iron are very important because they form a liquid at high temperatures, and this formation of this liquid allows the different reactions to occur much more quickly. Okay? So we have about 20%, and there can be other things we introduce to adjust it. So going back to this question of nomenclature, this is often very confusing, and you need to be clear about this because different people use different terminology. So first of all, we have the constituent elements, which are basically oxygen, silicon, calcium, aluminium and iron. These elements are all in the form of oxides, so usually that's why we use this abbreviation to refer to the different oxides. Calcium oxide C, as we've already seen, silicon dioxide S, etc. But really, we haven't got individual oxides, we've got oxides combined in different phases. A phase being a homogeneous region with a definite composition and crystal structure. And these are the phases, these are really what's important at the end of the day in our clinker. And we're going to come back to these over and over again. First of all, we have C3S. This is the most important. Tricalcium silicate typically makes up between 50 and 70% of the final cement. Then we have yeah. We have the aluminate phase, C3A, and we have the ferrite phase. Now, this ferrite phase is always written C4AF, but in fact, it's almost never C4AF because really it's a solid solution, more correctly written down here, where aluminium and iron can be interchangeable. So you can get actually a very wide variety of compositions going from about 2/3 aluminium to 1/3 iron to 1/3 alumina to 2/3 iron oxide. But you'll always see it written and always talked about as C4AF. So here's just some pictures to give you a quick idea of how things happen. This is the quarry. You have these large earth-moving machines. You blast out your limestone, you shovel it up, you put it onto your conveyor belt. It comes down to the cement plant, and there you very carefully blend everything together. So you take your limestone, you take your clay, and you may need to add in other things to correct your chemistry. And you grind them all together, and then you put them in this big hall. Okay, the idea of putting them in this big hall is that with all natural materials, you have little tiny variations. So what you do, you lay down your material in one direction, say this long direction, and then you take it in this cross direction. And by cross-cutting, this homogenizes the material, gives you a much more even blend. So this typically is the overall chemistry of a typical raw meal. And then that raw meal goes in the kiln. There's the kiln. Goes along, that's me in the cement kiln. It wasn't working at the time, in case because it was shut every year or so. You need to shut down this kiln because this kiln is made of steel, and to protect it from the high temperatures, you have to line it with bricks. These bricks last, typically 6 months, a year or so, and then you have to replace the whole thing. It comes down to the flame. So this is now your flame. And your flame has a temperature of about 2,000 degrees. And the hottest part of the kiln, the clinker, the raw meal, this is the raw meal here. You see it's coming down here. This goes up to 1450. Now, these temperatures are quite important. 2,000 is very important. This is why cement kilns can be very, very efficient for disposing of a lot of waste. If you have waste solvents, if you have waste oils, anything like that, you burn them at 2000 degrees, everything is decomposed. So it's a very good way of getting rid of a lot of solvents which otherwise might be quite nasty. 1450, because this is the temperature you need to go to get a reasonable amount of C3S, which is the material we want. So what we're going to look at here, we're going to look at the basic changes that occur in the cement kiln, and you don't need to worry too much about the steps on the way, but what's important is to realize that, this is what we start off with, our limestone, quartz, clay, etc., and what we're going to end up with here is the final clinker. And as we move along the kiln, as I said, the temperature is going to increase. This red line shows the temperature. And this is roughly the time going along there. So the first thing that happens, as we've already said, is the decalcination of your calcium carbonate with the emission of CO2, and you see you get this big reduction in volume as the CO2 is given off. So this calcium carbonate is transformed to calcium oxide. Then, as we go along the next part, we see this calcium oxide here combines with the silicate phases to give us, first of all, this phase C2S, which is also called B-light. Okay, so this is another part which is very complicated. You can guarantee in cement chemistry everything has got at least 3 names, and you have to know those 3 different names. And so we, at this temperature here of about 1200 degrees, we've got calcium oxide and B-light, and then as the temperature goes up, these two combine together to give us this material, which is what we want, which is the C3S or A-light. So you see at the end here, we've got A-light, about 2/3 of our clinker. We've got B-light, and then down here, you see we have this liquid, and this liquid then solidifies to give us C3A and C4AF, or ferrite phase. That's the clinker coming out. You see this is the grid that's used to cool it. You have air coming through here. You see these are the nodules of clinker, which is typically up to 1 centimeter in size, and then they go on to this thing here where they're allowed to cool down. Still very hot at this point. And if you cut one of those nodules open and look inside it, this is what you see. This is how you see where are those different phases. So the most important phase is this one here. This is your C3S or your A-light. And you can recognize this by the fact you've got nice faceted grains, because this was forming. This was the last phase that formed, so it's growing as nice crystals. And then we've got this B-light, the C2S, which was dissolving, because this was reacting with calcium oxide to give us the A-light, and that's why it's got this rounded shape. And then in between, you've got the material that was liquid originally, and this is now solidified to give us 2 phases. The very bright one is the ferrite phase, and in between, this is the aluminate phase. Okay? So this is basically what we end up with as the clinker. Anybody, any questions so far? No? So that's our clinker. We've now got to turn it into cement. And to turn it into cement, we make various additions. We always add calcium sulfate for reasons that will become clear later, typically about 5%. And nowadays we also add increasingly amounts of these other things, as I've already explained, because these lower the CO2 emissions, fine limestone, slag, fly ash, etc. This is a ball mill, which is typically used to grind up the cement. You see those are the steel balls that do the grinding. And then we end up with cement. So this is the grey powder. We all know what it is, more or less. If we magnify this up, put it in the scanning electron microscope, we see these are the cement grains. So what can we see here? Well, we can see that, first of all, we've got a big variety of sizes of grains. So this is a very big grain here, going down to very, very small ones. We see also that the grains tend to be agglomerated together. This is true of any powder. When you grind something up, you generate a lot of static electricity, which tends to hold things together. I mean, it's like dust, which forms great mounds in your house if you don't do the vacuuming every day. So this is the cement grains, and sometimes we can see that we've got small gypsum crystals on the surfaces. And then if we cut through those grains and see what are the different phases, what's very important is that we've got each grain usually contains several of the cement phases. So if we just go back to this slide here, when we grind the cement, it doesn't fracture neatly around the edges of these crystals. It fractures through these crystals. You can actually see these cracks here brought about by the thermal cooling. Okay, so you've got a big amount of thermal shock when you cool it, which causes these cracks, and then you see the fracture is going to go through the grains, and the different grains are generally going to have all the different phases in them. So when we come back to talk about these different phases, C3S, C2S, aluminate, etc., they're not existing in separate grains. They're all together in the same grain. What's the size? So we've seen there's this wide range of size. This shows the particle size distribution curve. We have a range from between 1 micron to about 70, 80 microns. We use an expression for the surface area which is very bizarre. Okay? People express the surface area of a cement in terms of what's called a Blaine surface area, which isn't a real surface area at all. What it is, you pack your cement powder into a little tube and you see how fast air flows through it. And then you make a conversion of that to surface area. Okay? It's not as stupid as it sounds, because the advantage of this surface area is it doesn't vary too much with kind of roughness of grains or whether they've got little holes in or things like that. So it's simpler to translate into a kind of a real idea of what the surface of the particles are. And you see, depending on how you do your milling, either you do an open circuit where you just grind the whole lot and keep it all together, or you do what's called a closed circuit where you recirculate the larger particles and grind them again, and in this way you can get broader or narrower particle size distributions. Yeah.
That short question, was it weighted by surface or weighted by number? Which weighting?
This is by weight. So you always do it by weight, which would be the same as by volume, because they all have the same density. But I mean, that's quite important, because when we come to want to modeling a cement, for example, as we're going to discuss on Thursday, we have very small weight here, but because they're small, there's a very big number of grains. And then finally, we've got our cement, and then we have to dispatch it. I think everybody has this kind of idea of a bag of cement, but today, in Europe especially, very little cement is actually sold in bags, less than 10%. Most of it, by far and away, most of it goes by bulk, either by these road transport or by trains. And again, you know, you've got to have in mind that you've got to make cement quite locally, because it's really only practical to transport it by road a distance of about 100 kilometers. Rail is more efficient. You can transport it typically 300 kilometers. And of course, the most efficient is boat, because you can go from one side of the Pacific to the other for the same price as 100 kilometers by road. So that's why a lot of cement plants are built at the edge of the sea. Right, so we've got our cement, and you know, we've got these different phases, C3S, C2S, etc. Well, of course, we want to know how much of these different phases there are in our grey powder. And up to quite recently, this was really a problem. This was really a problem because typically when you check the composition of cement, what you do an X-ray fluorescence test, which tells you how much of the different elements are present. And then these elements are transformed to oxides, and they're listed in a table like this. And you'll see looks completely random. You know, why do we start with silicon and then go down like this? Well, this is because originally this was all done by wet chemistry. It would take typically half a day to make your analysis. You would extract first of all the silica, etc., etc. Now it can all be done in a matter of minutes in an X-ray fluorescence, and this can all be automated in a cement plant. So you can take a sample, say, every hour or every 2 hours or whatever, and it will automatically go to the laboratory, go into the X-ray fluorescence machine, and you'll get your analysis every hour or 2 hours or whatever you want. Now, we see here that the main things are these four main oxides here. This typically makes up about 90% of the cement. And then we've got these minor elements which are kind of impurities in the raw materials. The ones that we've got to control are particularly the amount of magnesia, because if we have too much magnesia, this will cause swelling. Sorry, I didn't translate this from French. That means strict control to avoid swelling. We also have to control the amount of calcium oxide, which is not combined as other phases. So CaO3 lime basically means not combined in other solids. And so we've got this oxide composition, and what we really want to know is how much of these different phases do we have, because that's what's really important. And as I said, up until about 20 years ago, it was very difficult to do that, because the only thing we had to do that was what's called this Bow calculation. And still today, you'll see in most papers that they give you the Bow composition of the cement. Now, what does the Bow composition mean? Well, Bow basically came round and he said, well, look, how can we go from this to this? Well, what we'll do a calculation which basically says the only phase that contains iron is C4AF. We'll assume it has the composition C4AF. I've already told you that's not true, so that's why this doesn't work so well. One reason it doesn't work so well. We calculate how much calcium and how much alumina we need to go with that iron. We take those away from the remaining things. We see how much alumina we've got left over. We say that's in C3A, and so on and so forth. And you can express that all in these very complex equations, which take into account the different atomic weights of the different things and everything like that. The problem, as I've said, is this isn't very accurate, because the composition of the phases is not exactly this composition. For example, the ratio of iron to aluminium in C4AF can vary quite widely. In C3S, we can have about 1% of magnesium replacing the calcium, and so on and so forth. And typically, I mean, this is just an example, but this shows you how much the Bow composition can vary from the composition measured by quantitative X-ray diffraction, and you see it can really, really be quite big. And it's not systematic either. The differences are different from every cement. So nowadays, more and more, even in cement plants, you're doing the analysis by X-ray diffraction. I'll explain that technique more at the end of the day. But this is very important to realize, that when you're reading papers about cement and they give the composition, it's almost certainly the Bow composition, which is almost certainly wrong. And finally, we come in Europe to what we have in the European cement standard, the European cement norm, and it looks really complicated. Okay, so I mean, you don't need to remember all this, but what's important to see here is that this norm has been arrived at precisely to better be able to use these composite cements, these cements where we're adding in fly ash and slag and limestone. So as we go down, what basically changes is the amount of addition. We see at the top here, we see the CEM1, which is basically 95 to 100% clinker, with sulfate, of course. But even this CEM1 can have 5% of secondary addition, and virtually all cement you get in Europe today will have 2 or 3% fine limestone, because fine limestone, at this small level, it improves the properties and it lowers the CO2 emissions. So even a CEM1 will almost certainly contain small amounts of fine limestone. We then have SEM2, which basically has additions in the range up to about 35%. So often there's two levels, of one in the range sort of 6 to 20 and the other in the range 20 to 30. And these additions can be slag, these additions can be silica fume, they can be limestone, they can be fly ash, etc. So SEM2 is a blend with a fairly low level of additions. SEM3 are blast furnace slags. Blast furnace slags, as we're going to see, are in themselves reactive, and we can actually substitute even up to 95% in some applications. So you see the A, B, C are just higher and higher levels of substitutions. We then have pozzolanic cements, which are produced in Greece and Spain and Italy, etc., where they have pozzolanic materials. And finally, composite cements, which can have combinations of additions. So that's the end. I think we're more or less on time. Anybody any questions on cement production? It's quite a lot to keep in mind, but it is very important for what follows. So I hope everybody managed to follow most of it. Okay? So we've now, oh yeah, sorry, one question there.
Yes. Could you just repeat for my own notation the name of the different phases, because it was a bit fast for me to...
Yeah, okay. We're going to come back to this and we're going to see a lot of them in the next one. But, I mean, this is absolutely critical. So the four things we have, by far and away the most important is this one, C3S or halite. If you only remember one, remember that one, because that's, as I said, 50 to 70% of the material, and that's the stuff that really is behind 90% of the reactions. Similar to C3S, but as we're going to see, reacting slower is C2S. Okay, so it's the same, but it's got less calcium in it. And because of that, it's less reactive. And then we've got the two phases that are called interstitial, because they're in between these. Of these, again, the most important is the aluminate, or C3A. And of less importance, because it's not so reactive, is the ferrite phase, which we call C4AF. So C3S, C2S, C3A, and C4AF.